So I'm making this video to show a demonstration of a program I made that shows how various different search algorithms work in a simple state space. The state space is the map you see here, with VS denoting the start and G denoting a goal. Periods tell you that it costs 1 to move into them, and commas, which you can see on other maps, tell you that it costs 2 to move into them. So let's see how a couple of these algorithms work, and we'll slow it way down. Here you can see breadth first search, and it's checking all the lowest level nodes each time. In my follow-up videos, I'll be explaining how these algorithms work a little bit better. You can see the numbers here telling you where the algorithm is going to look next, and the black path shows you what path the algorithm is currently looking at. So in a second here, when breadth first search finds the goal, you'll see the black path shows you the goal, the path that breadth first search ends up taking from start to goal. The blue nodes show you the nodes that were looked at during this search. Here's depth first search, and we'll run it a little bit faster. You can see that it goes, instead of checking nearby nodes, it just goes straight down and then right and then up and then left. Those were just arbitrary direction choices. You could have it go up first or left first, whatever you want. You'll notice it got pretty lucky this time, and there are no locations that got searched that weren't on the final path. But it ends up getting a pretty long path as well. So here's iterative deepening search. And iterative deepening just does lots of depth first searches, but it says once I get to some certain depth, stop and try another depth first search with some maximum depth level set. So iterative deepening can take quite a while. There are some good computational reasons to use it in some cases though. This is A-star search. We can slow that down a little bit and show you again. A-star search is given some restrictions on the heuristic you end up using. The heuristic just tells you, your heuristic should give you an idea of how to rank nodes. So your heuristic should say if a node is closer to the goal, we prefer that. Bidirectional search that you saw at the end there just searches from the start and the goal at the same time. So now I'm going to run it really fast, and we can look at A-star on a couple of these different maps. You can see that the number of nodes that gets expanded is generally fairly low. You should keep in mind that other than the heuristic saying that some nodes that are closer to the goal are better than others, A-star doesn't know where the goal is. So this is an interesting map because it's actually impossible to get to the goal. So A-star search needs to check every single node, whereas bidirectional search immediately knows that you cannot get from the start to the goal because it can't make a path out of the goal. So you can see over here that the status has failed, the number of expanded nodes is 2, and when we run A-star search, the number of expanded nodes is way higher before it discovers that it cannot complete this map. Here's map 8. Map 8's a little bit interesting because the comma path, there's a shorter number of steps to get from the start to the goal, but it's higher cost. So here we look and we see the total cost of the final path was 16, whereas if we run bidirectional search, the total cost of the final path was 22. So that's my little program, and if you guys are interested, I'll do some follow-up videos explaining how these different search algorithms work in a little bit more detail.